Hello everyone, and welcome to a new video on the Hungarian method and Johnson's rule. We use the Hungarian method for scheduling problems and assignment problems. So we're interested we're going to be using it for assigning jobs to machines or workers, or assigning tasks. We could see tasks sometimes. Also, you could use the same scenario for assigning territories to salespeople and assigning repairs to repair crew. So what we're going to be seeing is basically a number of workers, as in this case, and a number of jobs, and we want to assign the jobs to the workers. So for example, here in this case, we have job A, when it's done by worker 1, is costing $8, and worker B does job 1 for $6, and so on, these numbers. So these numbers are costs associated for each worker doing the job. And what the goal of this is to have the most optimal assignment to basically minimize the overall cost. So, Hungarian method is going to be basically the method we're going to be using for assigning jobs by basically matching a job for workers to identify the lowest cost solution. And there's a procedure, a very clear procedure that we're going to go over that is going to help us find the optimal solution. So how does the Hungarian method work? So basically we'll have like a table of jobs, for example, job A, B, C, and then we'll have worker 1, 2, 3, and then we'll have all these numbers associated with some form of cost, and we're minimizing cost. So we're going to start by performing row reduction, which is basically taking the lowest number in this row and subtracting it from every member in that row. That's what we call row reduction, and we'll carry that table to the next step, which is column reduction. So column reduction, which is basically going to go over each column, find the lowest number in that column, and subtract every element in the column from that subtract that minimum number from the column from every element in that column. Then we do some optimality check. We check if we are at the optimality or not. Are we at optimality or not? Are we at the optimal solution or not? And what we were going to do, a series of long crossing lines that is going to basically cross the zeros. And we want to find the minimum number of lines needed to cross all the zeros, and we're going to show an example of how to do that. Now, if the number of lines is equal to the number of rows, then we reach optimality. If not, then we have to go to step 4. Step 4 is basically once we covered some of the numbers with lines, there's going to be other numbers that are not covered with these lines, and we're going to do some form of subtraction and addition. And then we check optimality again, and if it's optimal, we stop. If it's not, we repeat step 3 and 4. So this gets repeated. And if we reach optimality, then we start making the assignment. So very, very important is every table we calculate in Hungarian method, it carries forward to the next step. So we don't start from the original table. When we do assignment, we will refer back to the original table. So we'll have the renewed updated table, and the assignment will need both tables to make assignments. So let's see an example of how to do this. So we have this table right here. This is an example and it's an assignment. We have workers cost. So we have A, B, C, D as workers and X, Y, Z, W as jobs. X, Y, Z, W as jobs and workers as A, B, C, D. And we want to assign the workers to the jobs. So we start by what we call row reduction. And what we're going to do in this step is basically take the lowest number in each row. So this is one row. for example, and the lowest here happens to be 3. So we take note of that. So we take note of that it is 3. So we write 3. Then we go to this one, and this one here, the case is we have 6 as the lowest number in this row. And then this one, the lowest number happens to be 3. So we write down 3. And in the last row, we have 5 as the lowest. So now, once we do this, we just have to subtract each element from that. So we go each element within the row. So 8, 5, 3, 3, we have to subtract it from 3. So 8 minus 3 is going to give us 5. 5 minus 3 is going to give us 2. 3 minus 3 is 0. 3 minus 3 is 0. So we get these two zeros. And we do the same thing for the other rows. And we should end up with this table right here. Okay. Now this is the table we're going to use for our next step, which is the column reduction. So we're using the updated table. So we take each column now. So the first column here, and we take the minimum in this column, which happens to be 0. Then we take this column right here, and we take the minimum in that column, which happens to be 2. Then we take this column, and the minimum here is 0. And this column right here, and the minimum here is 0. Now we do the same thing. We take each element and we subtract it from the column minimum. No, we subtract from it the column minimum. So we subtract from it the column minimum. So 5 minus 0. So this column will remain the same because all the elements we're subtracting 0 from them. In this case, we're subtracting 2. So 2 minus 2. So here is 2 minus 2 is going to give us 0. 2 minus 2 again 0. And 6 minus 2 is 4. So we get these numbers. The remaining numbers will not be affected because we're subtracting 0 from them. So this is column reduction. So remember, in row reduction and column reduction, we're subtracting the row minimum from we're subtracting it from all the elements in the row. In the column reduction, we're subtracting the minimum value in the column from all the column values. So crossing the lines, optimality check, is a bit tricky because we want to find the row or column that has the most zeros. So we're looking at row or column with highest number of zeros. So we notice here that there is this row that has 3 zeros. That's a candidate. So we have this row that has 3 zeros. We see here that we have a column with 3 zeros. We have another column with 3 zeros. So we have a lot of options. We don't see any column with 4 zeros. So the highest number of zeros is 3. So we could choose arbitrary. So what we do is we start with our first row right here. We cross it out because it has 3 zeros. Then we could cross this column right here because it has 3 zeros. And we cross this column. And notice how we don't have any more rows or columns to cross. And that's very, very correct. So we've done the correct thing. We've got rid of all the zeros in the table. We crossed them out using these lines. So we should get this right here. Now, I'm just going to show you what happens if you're just crossing any line. So maybe you wanna, if you don't use the rule of crossing the highest number of zeros, if you start by crossing this here because it has 1 0 without taking into account that you have to start with the highest number of zeros, then maybe this one you would go next, and that's gonna give you 4 lines. And that's different from the real solution when you have to cross out the highest number 0. So this is wrong. You have to start with 3 zeros. Here's 3 zeros and here 3 zeros, so you end up with 3 lines. Because this is very important. Because if you end up with 4 lines, then you're at the optimal solution, because optimality says number of rows is equal to number of lines. In our case here, the number of lines is 3, and it does not equal the number of rows, which is 4, which means we haven't reached optimality. If you made the mistake of not following the rule and just crossing any line that you find zeros in, you might end up with 4 lines, and you might say that this is optimal when it's not optimal. So now that it's not optimal, we have to do what we call covering some values, and we're going to deal with the uncovered values and the covered values, and we're going to see how we're going to do this in the next step. So let's recap what we've done. We crossed the maximum amount of zeros in the lines, and we end up with a line which is vertical like this, and two lines, one line that is horizontal and 2 lines vertical. Now we end up with numbers that we call uncovered numbers. So these numbers are not covered by the line. No, they're not covered, uncovered numbers. While these, we will call these covered numbers. And what we're going to do here is and also very important is we want to identify intersection numbers. And these are where we have intersection point. And as we see in this right here, there's only 2 intersection points. So these 2 numbers here are intersection points. So we need also to identify intersection points. And the remaining covered values. But what's going to be very important is the intersection points and the uncovered point. We're going to subtract the smallest uncovered value from every uncovered number. So the smallest uncovered number, so we're looking at these 6 numbers, is going to be 3. We're going to subtract it from every uncovered number. And then we add the smallest uncovered number, which is this 3. We're going to add it to the 5, 0 here. So we're going to add it to the 5, 0. So we're going to add the smallest uncovered value to the intersection points. Now, if we want to do this, if we do this, we go 4 minus 3. We're going to do the first step, which is subtract the smallest uncovered value from every uncovered number. So 4 minus 3 is going to give us 1. 4 minus 3 again is going to give us another 1. 3 minus 3 here is going to give us 0. 4 minus 1, 1. 8 minus 3 is 5, and 4 minus 3 is 1. And we have all 6 new numbers here. And then we're going to take that 3, which is the smallest number in the uncovered value, and we're going to add it to the intersection points. So we're adding it to the intersection point. So we have 5 plus 3 and 0 plus 3. Let's use a different color here. So that will give us 8 and 3. 5 plus 3 is 8, and 0 plus 3 is 3. And this is our updated table. So this table is going to go with us for the next step of optimality check, another optimality check. Okay. So let's see this is our most updated table. We're going to be looking again for optimality check. And we're looking for highest number of zeros in column or row. Now this happens to have 2 zeros. This column here happens to have 3 zeros. And this column right here happens to have 2 zeros. So we're going to start with 3 zeros, right? Now also notice that we have a row with 3 zeros and a column of 3 zeros. Which one do we cross? It's arbitrary. It doesn't matter. So we could choose either to cross the row or cross the column. It will still give us the same solution. So we cross the row. Now we go next for the next line, which has the maximum number of zeros, which happens to be this one right here. So we cross it out. Then we have this one. Then we have this. So we have 4 lines in total. Now, very important, once we cross a line, we cannot go ahead and cross it again. It's only crossed once. So 4 lines of total. So optimality check. Number rows is equal to number lines, and in this case we have 4 lines equals 4 rows. We have arrived at optimality, so we're ready for assignment. The next step is assignment. So for assignment, we will start with the column or row with 1 0. So notice, I mean, the procedure is you have to really pay attention to all the steps in the procedure, not to mix them around. Here in this case, we're looking for a column or a row with only 1 0. Now we see a column row here, but it has 2 zeros. We see a column here, it has 3 zeros. The only row or column that we could find that only has 1 0 is this row. There's no other row. And you could pause the video and check it for yourself. This is the only row that we have 1 0. Also, so maybe there's this column here. Yes, that's true. There's another column that only has 1 0. So we could have started with the C column. So we'll start with the W row, and we have 0. 0 in this case, so 1 0. So let's make our first assignment. So we have 0 here. It's A and W. The 0 corresponds to the A and W. So we know job W needs to go to row to worker A. So we know that job W is going to go to worker A. So now we cross out both the column and the row. So we can no longer have these considered. They're done. A is assigned, W is assigned, done. Now we go on to the next step is we need to find the row or column with 1 0. So I find this. There's probably this column right here. The other column, you could have chosen this one, but I mean arbitrary. If it's 1 0, then it's up to you. You choose whatever one you like. So 0 1 1. So in this case, where the 0 is where the assignment is going to take place. So this is where the assignment is going to take place. So we have 0. So B is going to be assigned to Y. Sorry. So B is going to be assigned to Y. And let's say we make job Y assigned to worker B. Okay. So now we basically cross out this row here and this column. We can no longer use them because we already made the assignment. So the next row with only 1 0 is this row right here, is the Z row. And where 0 is the D worker. So D needs to be assigned to job Z. And from this point on, we no longer have to do anything else because we know there's only one job left, which happens to be X. and one worker, which happens to be worker C. So X is going to go to C because there is no jobs left but that job, and there is no worker left but that worker. So we just made the assignment. So let's recap the making the assignment is you have to start with column with 1, 0 or row with 1, 0. And remember, we're crossing out column and row at that element that we choose. So that's how it works.